Welcome to Brain Vision.
Once again, welcome to a new problem. This time we have two cars were given, two cars driving in opposite directions. You have a bigger car with the mass, I'm going to call it MA, happens to be 1750 kilograms, and then it has a velocity VA, which we call the initial velocity, moving in the right direction. It's a positive velocity, so that's going to be 1.5 meters per second positive. That's what we're given. And then we're also given a second car. We're going to call it B, and it's driving towards the left. It has a mass of 1,450 kilograms, and then it has an initial velocity in the left of 1.1 meters per second, but we're going to have it as negative because it's moving in the opposite direction. So this is positive and that's negative. The other thing that we're given is that these two cars are going to bump onto each other. So there's going to be some bumping going on. They'll collide. Okay, so this is kind of like the before and then after. Afterwards they collide. So this is the second car. When they collide, the final velocity of the first car is still in the positive direction, but this time it's reduced to 0.25 meters per second. For the other car, after collision, so we're saying this is what happens after collision. It's going to be going in, so both of them are now traveling in the same direction. So the final velocity of the second car happens to be, if we check that, we don't know what the final velocity is going to be. So that's what we need to find out. Okay, we want to find out what happened afterwards. And then also we want to find the change in kinetic energy. Okay, remember there's no friction in this scenario, so that means we don't have any losses of energy in the system. So the fact that there's no friction, the momentum is conserved. Okay, we have conservation of momentum. That's what's going on in this case. Change in kinetic energy simply is the final kinetic energy of the system minus the initial kinetic energy of the system, and that means we have to account for both the kinetic energy of the two cars. So we're going to kick off on part A and see that we're applying the momentum after collision happens to be exactly the same as the momentum before collision. And so the momentum after collision is the mass of A times the final velocity of A plus the mass of B times the final velocity of B, which is the second car. And then before collision, we have the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B. Our goal is to find the final velocity of B, which is the second car. And we know it's moving. We're going to see how it's moving. It could be moving towards the left or towards the right, just depends on the sign of the solution. So this is MA VAI plus MB VBI minus, so we're moving this one to the right, MA VA final. We have all that information, and we want to divide everything by the mass of B. That gives us our final velocity of B. For purposes of writing the numbers in the problem, we're going to jump into the next page to get the the final velocity of B of the second car. And if you can see from that, we have the mass of A, 1750 kilograms. Okay, we have 1750 kilograms times the velocity of A, which is 1.5 meters per second, the initial velocity of A, 1.50 meters per second. And then also we want to add the mass of B, 1450 kilograms times the velocity, initial velocity of B, 1.10 meters per second. And then there is also another portion of the problem which needs to be subtracted, and that happens to be the mass of A and the final velocity of A. The mass of A and the final velocity of A. So we're subtracting that 1750 kilograms times the final velocity of A happens to be, if you go back on this side, 0.25 meters per second. 0.25 meters per second. And all of that is going to be divided, as you can see, by the mass of B. Always a good habit to leave the variables up until the end. So this is 1450 kilograms. When you plug in the numbers, you find that the velocity of the lighter car ends up being 0.408687. So let's just make sure that this is the right process. So we have 1750 times 1.50 plus 1450 times negative 1.10, and then minus 1750 times 0.25. So then we have to divide by 1450. And that gives us 0.4086. That's the final velocity of the smaller car, and it's positive, meaning that it's moving towards the right, meters per second. Remember, we're still under the law of conservation of momentum. Okay, and so that's what we're using in this case. In the second part of the problem, that's part B, we're going to see how the change in kinetic energy happens. That's just the kinetic energy final of the system minus kinetic energy initial of the system. And so the final kinetic energy is the final kinetic energy of the bigger car, which we're calling A final, plus the final kinetic energy of the smaller car, minus the final initial kinetic energy of the bigger car, plus the initial kinetic energy of the smaller car. So that's the process right here. So this is 1/2 ma v a final squared plus 1/2 mb v b final squared, minus, always use brackets when you have to, 1/2 m a v a initial squared plus 1/2 mb vb initial squared. So that's our change in kinetic energy. We can simplify the whole thing by moving things around. So we have 1/2 ma va final squared. This one right here, we're going to put them together, minus 1/2 ma va initial squared, and then we bring this on, plus 1/2 mb vb final squared, minus 1/2 mb VB initial squared. So what we're doing right now, we're doing algebra, we're doing a distribution of the minus to both of them, and then putting all the A's and all the B's together. There's a big 1/2 outside, and then we have MA VA final squared minus VA initial squared plus you have to change this part right here because it's a single. We pulled out the 1/2 outside because it shows up in all of them. So we want to have that. So this is plus MB VB I should have called this VB final. So it looks like something a little bit different. It's a subscript though. So we have to bring it back down there, a final squared like that. We get rid of this one right here, this square. We only need the single one. So in this case, VB final squared minus VB initial square. Don't forget that square right there. And that's our whole problem. Next part is we just need to plug in numbers. We could use the difference between two squares if you wanted to, but again, that's optional, up to you. So the change in kinetic energy becomes equivalent to 1/2. We plug in the numbers. Mass of A is 1750 kilograms, and then we plug in the final velocity of A, which is 0.25 meters per second. You want to square that result, so we have to be very focused on how we simplify this. This whole thing is squared, and then minus the initial velocity was 1.5. That's for A. You could see the initial velocity was 1.5 meters per second. And that's also going to be squared. And then we go back, we see we need a plus mass of B, which is 1450 kilograms. And then the final velocity of B, we need to get the final velocity of B, which is 0.4086. 0.4086 meters per second squared, minus, if you go back, initial velocity of B, that's at the beginning where we see it's negative 1.10 meters per second. Negative 1.10 meters per second, and we also need to square that. When we plug in the numbers, we get to see that the final so we have 1750 minus that. We simplify, this is 1.5, and so the final becomes negative 2670, around about 0.3 joules. Okay, so this is the change in kinetic energy. That's the change in kinetic energy that happens when you have two cars moving in the opposite directions and then they bump into each other. Okay, so negative 267.3 joules kilograms. Hope you enjoyed the video. Feel free to share any questions or comments. Looking forward to talking to you in the next video, and have a wonderful day. Okay, bye.